Welcome to the second lecture of our 310 course. And so, if you'll recall that I mentioned that the first couple of lectures, so certainly this lecture and the next lecture, and possibly a bit of the lecture after that, will be devoted to reviewing important concepts from 309 that will be used throughout the course. As I mentioned to you, I'm going to go through this extremely quickly. So, I encourage you to, if there are gaps that you're seeing, to to recover, to try to fill in those gaps yourself. But this is hopefully a refresher that's going to kind of remind you of some of the key concepts. So what we're going to do today is go through the key distributions from 309 that are going to kind of come up quite a bit in this course 310. So by the end of today's lecture, I'm going to kind of use terms that use distributions like you saw the Bernoulli distribution in the previous lecture. I'm going to use this and 8 other distributions that you learnt in 309 pretty consistently, assuming that you know what they are. So just to make a couple of quick announcements. So the first homework has been posted on the Canvas website, and it's due Thursday, September 11th. And I guess another thing that I forgot to mention before is that in the file section on Canvas, there's a weekly schedule, so you can get a rough idea of what will be covered in the lectures to follow, and that will also refer you to the relevant chapters in the textbook. So in particular, today we're going to cover important distributions from 309. I'm going to try to tell a little bit of the story behind those distributions, kind of where they come from, and why they're useful and some of their key properties. So in particular, there's 9 distributions total that we're going to cover, and these will all be distributions that will be used quite a lot. So in particular, for discrete random variables, there's 5 distributions: Bernoulli, binomial, geometric, negative binomial, and Poisson. And for continuous, there's going to be exponential, gamma, uniform, and normal. And we're going to cover all of those today. So let's begin with discrete random variables. And once again, I repeat that I'm going to cover these concepts very quickly. So discrete random variable, so we say x is a discrete random variable, and it's discrete if its range is discrete or countable. So what I mean by that is the range, for example, could be just a finite set of numbers, like in the Bernoulli case where it's just a 0 or a 1. It could be any integer, but it can't be some uncountable continuous range. And a discrete random variable is defined by its probability mass function. This is a function that takes in some value of the range, and then spits out some positive number between 0 and 1 that indicates a probability. So the sum over the range is equal to 1. So we have this property that and just some key facts about discrete random variables. You can calculate the expectations and the variances in this. You can calculate the expectation and the variance is in using this formula. So for the expectation, we get that the sum of the we take the sum of the PMF times K, which is like a weighted average, and then the variance, which measures the variability, is just the squared difference between K and the overall mean or expectation. Okay, so now I'm going to cover the key distributions that we're going to see in the course. And I think it's always important to keep in mind sort of where these distributions come from. So what's kind of the story behind these distributions. And in particular, for the first 4 distributions, the Bernoulli, binomial, geometric, and negative binomial, they can always be related back to Bernoulli trials. So the way to think about Bernoulli trials is Okay, so the way to think about Bernoulli trials is a series of independent coin flips, but the coin potentially is biased, and P is the probability of a success or a head or a win. So you essentially, each Bernoulli trial is just a binary random variable. It's like a 0 or 1. And then P is the probability of success. And so we're assuming that these coin flips are independent. So And so these correspond to a number of situations. So in particular, we already saw one in the previous lecture of voting, where you have a binary random variable indicating whether someone votes Democrat or not. And you can also think about wins or losses in sport. And there's lots of different questions or scenarios you can try to model. So, for instance, you could Okay, so as I mentioned, there's a number of different scenarios you can look at. You could look at just a single trial and whether that trial is a success or a failure, and that corresponds to a Bernoulli random variable. You could look at multiple trials. So, for example, if you take a sample of like 100 people, or if you think about a season of 16 games, you can look at multiple trials and count the number of successes, and that's a binomial random variable. Another thing you can look at is looking at the number of failures until the first success. So this is kind of really important if you think about, as soon as a success happens, you basically stop, or as soon as R successes happen, you basically stop. And so for a single success, this corresponds to a geometric random variable. And for R successes, this corresponds to a negative binomial random variable. So we're going to first cover the simplest discrete distribution, the Bernoulli random variable. So as I mentioned, this is just a single trial. And so what's the range going to be if we think about that? And then, the range, is just simply, it's either a 0 or a 1. It's a 0 if you have a failure and a 1 if you have a success. And then if we think about the PMF, then this is just going to be, there's only two values we have to think about, 0 and 1. The probability of a failure is 1 minus P, because P is the probability of success. And then the probability of having a success is obviously just P. And you can see that this adds up to 1. Okay. And then the other thing, and we actually used this calculation in the previous lecture, but we'll go through it here. So we have that, E of X is equal to And then the variance, you can do a similar calculation to show that the variance of x is equal to p times 1 minus p. So I actually used all these calculations in the previous lecture without explicitly kind of going through them. These are things that will actually be provided to you on a sheet, so you don't need to memorize these or to necessarily be able to calculate them, although you do need to understand sort of the fundamental principles. But you can imagine that I'll refer to a Bernoulli random variable throughout this course, and just some notation that I'm going to use a lot today and for the rest of the course. This indicates a random variable has the distribution Bernoulli with a parameter p. And once again, I did actually use this notation in the previous lecture, but now now that we're trying to be a little bit more formal, we're going to state this notation explicitly, and I'm going to use it for the remainder of today's lecture. So the next thing we're going to look at is the binomial random variable, which is just n independent trials. Okay, and so each trial has a probability p of success, so we can use the notation x is binomial NP. So we could have actually modeled the voting scenario where you have a sample of 100 people like a binomial with n equals 100. We ended up just using the central limit theorem before, but we could certainly use a binomial distribution to model that. As I mentioned, you could also imagine that if you have a 16-game season and you want to see how many wins you have, that could be binomial 16p. So we have two distributions. And so once again, what's the range of x going to be? So which is, what's the small, what possible numbers could you get? And you could either get 0 successes, 1, all the way up to n, okay? And so this is going to be our range, and as you can see, this is discrete. And as I mentioned, a PMF, a discrete random variable is defined by its PMF. And so you can actually show that the PMF for this random variable has a nice explicit formula, which is given by this. So we have, n choose k times p to the k times 1 minus p to the n minus k. And, again, this is a formula you could just remember, but you could also, imagine deriving it. So you have n trials, and you imagine that in those trials, there's p successes and n minus, that there's, if x is equal to k, that means there's k successes and n minus k failures, and that's where the p to the k and the 1 minus p to the n minus k come from. And then but then this can occur in n choose k different ways depending on where those successes and failures are. So that's where this formula comes from. Okay, so now if we focus on its expectation, you could certainly calculate this explicitly, and it's possible to do that using the binomial formula, but I think it's, this is a formula that, will be given to you, and I think it's good to intuitively just try to, remember this, that expectation of x is just n times p. Remember that for a single trial, the expectation is p, and here you have n trials, and so you can think about, the probability of there being, the expected number of successes is going to be n times p. And similarly for the variance, once again, we just multiply by, Sorry about that. Once again, you just multiply by n to the Bernoulli case. And in fact, you can kind of make this a little bit more precise, or make this calculation a little bit easier. If one natural way to generate n independent to generate a binomial random variable is with n independent Bernoullis. So, and we actually did this indirectly in the previous lecture as well. Okay, so we can say that if you have n independent Bernoulli random variables, if you sum them up, you get a binomial random variable, and that makes this calculation of both expectation and variance pretty, pretty simple and pretty explicit. Okay, so remember that the geometric random variable measures the number of failures until the first success. So once again, there's only one parameter of interest here, which is p, the probability of success. And just like I've done before, the range that we should be thinking about is what are the different values this can take. So you could have 0, if you get a success on the first go. You could have 1 if you get a failure first and then a success. And then 2 up to, as large as you want, depending on how many failures you get until that first success. And so this, once again, even though it's infinite, it's a discrete random variable because this range is clearly a countable set. And the probability mass function, you can calculate in a pretty straightforward way. Is you just have k failures and then a success. So sorry for that messy. Yeah. So you have k failures and then a success. So it's just 1 minus p to the k times p. Once again, you can do some algebra to calculate this expectation and variance, which I'm not going to do because once again, these formulas are going to be given to you. But you can kind of intuitively see that as p gets bigger, this expectation kind of gets smaller because the number of failures you have is going to get, is going to likely be smaller. If your p is like 1, for instance, then the expectation of x is 0 because you're never going to get a failure. And if p is 0, this expectation kind of goes to infinity because you're just going to keep getting more and more failures. And the variance, once again, is a calculation you can do, but once again, you can see that if p is 1, your variance is 0. And if the smaller and smaller p gets, the larger the variance. So recall that the negative binomial is it's the number of failures until you have r successes. So this actually has 2 parameters. R and P, and I use the abbreviation NB here for negative binomial. One key thing to point out is, can you potentially see a relationship between the negative binomial and any other distribution? So the geometric's the number of failures until 1 success, and here counting the number of failures until r successes. So what you can hopefully see is that you can generate your negative binomial from R independent geometrics. And so I'll write down the formula for the PMF. So first of all, sorry, let me. The range just like the geometric, you can have any number of failures until R successes, and then the PMF. Okay, so what you can kind of see that will hopefully be clear is you're going to get 1 minus p to the k times p to the r, because you have exactly r successes and k failures. But then you have to kind of count the number of like sequences of failures that you possibly have. And so the way to do this is to say that you know that on your first r plus k minus 1 trials, there must be exactly k failures and r minus 1 successes. So this is the formula that we get for the negative binomial. Okay, so now I'm going to give you an example, and just like all other examples, this would be the time where after I read the example, I'd encourage you to pause the lecture for about 5 minutes, try it yourself, and then come back. So here we're going to go to a classic old example. Most of the examples in this course will not be as, I'd say, mundane as these dice examples, but I'm going to use these dice examples because we know what exactly the probabilities are. So you roll a fair six-sided dice, and then we're going to say find the expected number of rolls until you get a 2. And for part B, you're going to say if you roll the dice 10 times, what distribution would you use to model the number of 2s? Okay, so go away and think about it for 5 minutes. So stop the video lecture and think yourself. And then I would say you should restart the video lecture. Okay, so we want to find the expected number of rolls until we get a 2. So to put this into a formal framework, we say X is the So x is the number of rolls until you get a 2. And so you're pretty tempted to say that x here might have a geometric distribution. And then the probability of rolling a 2 is a 6, so it's geometric of 1/6. But the other thing you have to be careful of here is that we're counting the number of rolls. We're not, like, remember that the geometric distribution, as I've defined here, is the number of failures, so the number of non-2. So all we have to actually do is to add a 1 to this. For some of you, like, you may have also seen another definition of the geometric, which is just the number of trials or the number of rolls, which would have that 1 automatically in there. The range there would go from 1 to infinity rather than 0 to infinity. But I'm going to stick with the definition here where it starts at 0. So that means that for examples like this, I need to add a 1. Okay, so here we, and we want to find the expectation of x here. And so that's just going to be 1 plus the expectation of geometric of 1/6, which is just going to be 1 minus the 6th over 6th, which is just going to be 1 plus 5, which is 6. And it's a good idea to just check if the answers you get kind of intuitively make sense. If I told you that, how many rolls would it take to get a 2, 6 sounds kind of reasonable because, you only have a 1 in 6 chance of getting a 2 on each trial. So for part B, here we're going to use x. I guess it's a different x here. So maybe to be clearer, I will just use a different letter of y. Number of 2s in 10 rolls. So what distribution do you think might model this? Here we have some number of trials, 10. And so that should already give you a clue that this is going to be like a binomial. And indeed, it's going to be binomial. And you have to specify the 2 parameters of the binomial here. And it's 10, which is the number of trials. And then a 6th is the probability of getting a 2. So that's just an example to kind of give you a scenario where you might expect to see these Bernoulli trials. So the next set of distributions arises from a different scenario, which is, and so in particular, what I'm going to refer to as the Poisson process. This is can be thought of as events occurring in continuous time. So just to give you some concrete examples to think about and have in your mind, you could have situations like, storms, or earthquakes, social media posts, but what we're trying to say here is that you can think of a social media post or a storm or an earthquake as some event that just occurs at a point in time. And this can be thought of as you can model this potentially as a Poisson process. And so what we have here in general that sort of ties this together is that we have, just like for the Bernoulli random variable, we had like a probability of success. Here we have a parameter lambda, which is greater than 0, which is like the rate or intensity at which events occur. Okay, and so what you can think about this is over a unit time interval, which for storms or earthquakes may be a year. For social media posts, maybe it's a day, maybe it's a week, depending on how active a user you are. This is really the number of events that occur over a unit time interval. So you can think of this as average number of events over unit time interval. Okay. And there's a few different things we can model. We can look at you can look at the number of events over a unit time interval. This is a Poisson distribution. And since, as we'll see, the number of events is a discrete number, this is a discrete random variable. You can look at the waiting time until the first event. And this is, in fact, an exponential random variable. And this actually moves into a continuous random variable because time here is continuous. And then the waiting time until R events occur, and this is a gamma random variable. Okay, so the final discrete distribution that we're going to cover today is the Poisson distribution. So this is the number of events that occur over a unit time interval. So here we have that x is Poisson lambda. So lambda is the rate or average time, is the average number of events over that unit time interval. So the range here again is just zero, the integers 0 to infinity. You could have no events, one event, two events, and so on. And the PMF, and again, I'm just going to give you the formula. So this is the PMF. You where that formula comes from is not super like intuitive if you just see that formula, but hopefully it rings a bell from 309. Just to give you a little bit of intuition behind it, you can think about it in terms of if you imagine that you have a binomial random variable where you have kind of n events, where you have kind of n slots over a unit time, lambda over n is the probability of there being an event over a particular time period, and you assume that this n's getting very big, you can actually show that xn, this is a term we haven't defined, but was covered in 309, and we will go through it in the next lecture. Xn converges in distribution to x. So the reason I'm pointing that out is just because one way to think about where that formula comes from is if you imagine a binomial random variable where you chop up a unit time interval into n bins, where the probability of an event occurring in any bins is lambda over n. As n gets bigger and bigger, so you can think about that as becoming continuous time, and you get exactly this PMF. So this is kind of why you get this distribution. So the expectation, once again, you can do the math here, but I'm just going to give you the formula. And the best thing for you to take out of this is just the intuition. The expectation is just lambda. Remember that the definition of lambda was the average number of events over a unit time interval. And the Poisson random variable is modeling the number of events over a given time interval. So the expectation of average is just lambda. And then the variance is just lambda here. Okay, so I think now is a good time to take a short break, and we'll return with continuous random variables after the break.